So that brings us to the last step of the structured electronic design of negative feedback amplifiers, the design of the bias sources themselves. So, and then we are here. And now what you see again the house of quality here in this thing. Because what we are basically going to do, let's say, look at the design. Let's look at the design. Sorry, here. We have 1, 2, well, call this 1, 1, 2, 3 bias sources. And we have requirements for them. So the first thing we do is set up requirements. And then we have, instead of 3 amplifiers, we have 3 bias sources to design. So you can find your requirements already on this level, or even earlier in SlideCAD. Because if you want to know what is the noise budget for I1, you just add a noise source here and transform it to equivalent input and see what is the noise contribution. But you can also say, if this is a unity gain current amplifier, then I might place as well this noise source just here. And then you see if this is the same noise as M5, then probably the current noise of M5 will be doubled if this transistor is exactly the same transistor, having the same GM and the same current. So that's why the noise needs margin, and maybe we already know that this must be made in a smarter way than just putting some transistor there without thinking too much about it. Similar thing can be said here. If this is a voltage source, well, let's say if the impedance of the voltage source is large, maybe at high frequencies, then definitely if this impedance will cause a frequency, will be part of the transfer, because the transfer was set by C1. So in order to have more budget for the impedance of V1, I might as well tie C1, this side of C1, directly to the output. That would be better. Then I have more margin for V1. So at this level, we can think a lot about the specifications and derive specification for all the bias sources. And that's what we are going to do. Oops. I need to go through all my things again. So we are going to specify the bias sources. And basically we start the whole thing again, because if this house of quality, if this works for amplifiers, it also works for bias sources. Let me see what happens here. With the specification for bias sources, we just go there and it is setting up the specifications, but now for bias sources, and we just go on like here. Now, of course, a bias source is not a 4-terminal element. But in many cases, we make a, for example, current source by starting with a voltage reference and making a transadmittance amplifier. You could even model a current mirror as such if you only use it for biasing. One transistor is making the model and a voltage from a model, and the second is converting the voltage for the model again in a current. So the second is just a admittance amplifier, and the other one is a voltage reference. Well, for a voltage reference, you can also set up specifications. So we are just following the same procedure. That means for every bias source, you go through this. And if a bias source needs to be biased, you do it for every bias source of a bias source. And if this bias source needs to be biased, you do it for a bias source of a bias source of a bias source. And this makes this a hierarchical design method. You can even start here at system level, and then maybe you need more generic terms because you are not generating building amplifiers, but you still have a kind of the same structure all the time. So if we are, let's say, now you see here, what is happening? Well, I need for the bias sources requirements for noise, for drive capability, a current source must be able to take some voltage. That is what we have discussed in the realization of current sources with passive elements. We need a passive element that behaves as a current source. If it is passive, then in the origin it will always have a resistive behavior. And then it will maybe the characteristic, the VI characteristic, will saturate to some kind of constant current characteristic. So there will be drive requirements for the bias sources. The bandwidth, if the impedance, you could say this is more like the impedance of the bias source and the frequency response of the bias source. Can it have, if we have biasing and it is only required in a limited frequency range, our amplifier to work, then maybe our bias sources can have parasitics. Maybe we can even use electronic inductors for that purpose. So if the bias, the specifications are not good and we're not going, then there is an influence with the previous steps. So this means that experienced designers, before they start designing the amplifier, already make sketches about what kind of biasing structure will be at the end. But what you also see in daily design practice, because everyone is working either completely in LT spice or in cadence, that you have to work with the biasing all the way, because you cannot do any noise simulation without the biasing. And that is the advantage of slide cap. We only need to do the biasing at the moment we need it. At the moment we need to talk about nonlinearity. Then we need to go to another simulator, a numeric simulator that needs biasing. Otherwise we don't need it. And that saves a lot of time. As you have seen, we can do the whole structure design, the whole design of the amplifier with the signal path without really calculating the bias points. No, we need relation between geometry, bias point, and small signal parameters. And those relations are captured in slide cap. So, these are the bias sources. Find an operating mechanism. That's the principle. We need to find an operating mechanism. So if I need a voltage source, I need to have a passive element that behaves, that has a voltage source character. Let's say if I change the current, then the voltage doesn't change so much. That's what we call a voltage source character. Current change, current source character, the opposite. If I change the voltage, the current doesn't change that much. So we need to find some mechanism. And so either an element with a voltage character or a current source character. Then we need to know in which performance with the A, as this is an error, I'm sorry, in which this performance aspects of the can be affected by design, just as we did with amplifiers. That's why we studied the CS stage extensively, because we wanted to know how can we affect the design, the performance by design. And we found out, for example, that the noise can be affected by design by changing the current or the width, in fact, by changing the GM of the device. And FT can be done in the same way. That's what we have studied, and that's what we will do also for bias sources. And if then after we have designed it as good as possible, it is still not good enough, we can use error reduction technique. We can make a complete feedback amplifier to make a perfect current source. That is, converting a voltage reference into a very accurate current with an extremely high output impedance that does not depend on temperature. Basically, it's an amplifier, which you are then designing. And that's why you go to the complete path here.